I already have discussed the analog design considerations. So one of the major consideration is dual rail. That means the voltage can go to positive as well as in negative. So this is not the case for say digital design, but in analog you have to take care of this. One of the important thing is the biasing, because biasing it may lead to a critical problem, which I already have said, that if you are in linear domain and if you are not biasing the whole thing in a proper way, it may happen that a portion is going to the non-linear zone, which will create trouble. So biasing is always important. Apart from this, now biasing also decides that how much power is going to be consumed. So if you are biasing it with a higher current or higher voltage, power dissipation will be higher. However, this may give you some sort of advantage in terms of gain or something, but ultimately you are going to lose the power, and power is one of the major parameter nowadays. If you see different devices, they want the whole device, for example, say your smartphone. Everybody wants the smartphone to stay alive for say at least 24 hours, 48 hours, if possible maybe a week. So it depends on the power dissipation, right? So there is always a requirement. So biasing is a very critical parameter while you are making some circuit. So although I have said here that analog design consideration, we are not going to design something. So this course will specifically deal with the analysis. I mean, this is the first step towards design. So you'll get to know what are the different aspects of analog circuits that has to be considered when you are designing something, designing an analog circuit, right? So although it is written design, we will do mostly analysis. However, in there are advanced course where you will also learn the design, but before going to that course, you have to be prepared with the different types of analysis. Otherwise, you won't understand. Anyways, so the biasing is also important. This is an important parameter. The other thing is linearity. What is linearity? I already have said that you have to operate in the linear domain. Otherwise, you may encounter higher order parameters, or sometimes say if it is AC signal of sine omega t, say V0 sine omega t, L comes sine square omega t, and you will end up with say 2 omega, 3 omega terms, which are the harmonics, which is not required in most of the cases, but you will lose a lot of power for those harmonics. So one of the major goal is to suppress those when it is not necessary. There are different circuits available. People may argue that let it be there in the circuit, we will use another circuit to suppress that. But the point is, if you are increasing another circuit, again the power will come into the picture. Why you want to power a separate circuit for suppressing this separately, if it is possible in the design itself? Okay, then there are a lot of issues, but the point is, the target is to suppress the higher order parameters, or say the harmonics. If it is possible without any external circuit, this is the best possible option. Then you have noise tolerance. As I have already said, that noise is always a matter of concern in circuit. Sometimes even the noise is not external, the circuit itself may generate some noise. So this becomes a problem. For example, if you have a 5-stage amplifiers, so each stage will generate some sort of noise, and it will amplify the signal. And while it is amplifying the signal, it may happen that it is amplifying the noise as well. So the noise in the first stage will go to the second stage, will amplify. Now that noise will go to the third stage, and the noise from the second stage also going to the third stage. In that way, the noise will start increasing. So you have to have a system, or you have to have a process wherein the noises are not transmitting, only the signals are transmitting. That way you can reduce the noise. So that is why I say noise tolerance in the circuit is required. Now there is another term called low drift. So low drift means the drift should not be high. Drift means it should not uh, go away from where it has been set. For example, if you bias something with 2 volts, okay, say this is constant 2 volt, that is you have biased, and this is time. Now you are seeing that with time it is drifting down. This is not desirable. Say 2 volt has become 1.6 volt after some time, then there will be a problem in the circuit, especially analog circuit will suffer. So drift is an important parameter. So it did not be the drift of this kind of voltage parameter. Drift may also happen because of external parameters like temperature. Now each circuit has power dissipation, some sort of power dissipation. It will increase the heat in the circuit. Now once heat is increasing, you will find that your voltage, current, everything is drifting from here and there. So this also has to be taken care of. There are circuits where generation of heat is higher. In that case, you may need heat or temperature compensation circuit or something through which you can control this drift thing. So it's not always the circuit thing. The external say temperature, humidity may also induce drift into your circuit. So you have to take care of all of them. Then there are no standard blocks available. This I already have said that for each system you have to design your circuit from the beginning. So there is no standard block, something that you can bring in and directly can couple and make another circuit. It's possible in digital. So digital people may provide you say a special multiplexer, adder, these things, and you can bring them and can make another circuit for certain application. But in analog it is not possible. That's why intellectual property creation is very difficult in analog. In fact, you cannot create, because each system has different circuits. So how can you say that I have a circuit for this application? Because it's not the case. But in digital, maybe you have designed some multiplexer which can be used for this application. So you can say it's my intellectual property. So standard blocks are not available for analog. Then another consideration is low voltage and low power circuits, which is always a requirement. However, when you use low voltage, low power, it also is related to the biasing. So they are all interconnected to each other. You may want a very low power, very low voltage circuit, and your biasing will be very less, and you will find that your gain is also very less. At that point of time, you will suffer. So you cannot just make something very small or something like that of your choice. It depends on the circuit and device characteristics as well. So the next thing that I have said was the parameters like transconductance. This is one of the important parameters. I have said output resistance is also an important parameter. I have said then input referred noise is also a important parameter. Why I say input referred noise is, people expect to take care of the noise in the input level itself. Although you will see the noise in the output, but the considerations has to be taken in the input level itself. So input referred noise is also important. Another important is the bandwidth. So you want an circuit to work for say 1 gigahertz, 1 terahertz. Although it's a overstatement, 1 terahertz and something like that. It's very difficult to make. So there is a relation called gain bandwidth relation. So gain bandwidth relation is something like gain and bandwidth multiplication is constant. Although this can be violated by external circuits, there are ways, but generally it is said that gain and bandwidth, product of gain and bandwidth is constant. In that case, if you want a high bandwidth, so 1 gigahertz, you will find your gain is very less. Now, if you are designing an amplifier where gain is say less than 1, you can't even say it's an amplifier. So typically in megahertz kind of thing, it's still okay, but for gigahertz and terahertz is very high. So in that case, you will compromise the gain to a level wherein the meaning of designing the circuit is not there. Okay. So you need an adequate amount of gain, and then you need a good amount of bandwidth. So this is the trade-off, right? One thing you want to increase, for increasing gain, again you have to increase probably GM, which is related to GM gain. So if you increase GM, you have to increase IC, which is related to biasing. Now if you're increasing IC, you lose the power. So it's all interconnected. You can't work on a parameter separately, or you keep it isolated and improve it won't happen. All of them are related to each other. So when we say a noise in the system, so I already have discussed, in analog the noise is something like this in the signal itself. So each ripple here maybe in the output may become very big, okay, which is very difficult. However, in digital, if you have a threshold, you'll find these type of ripples are, even if you don't care, it's okay. So life is simple in that term. But in analog, life is not as simple as digital, at least as far as this problem is concerned. So noise is also an important parameter. So you have to take care of noise. So there are different types of noise. Now, two important or very known types are thermal noise and 1/f noise. So if you look at the noise versus frequency, noise voltage versus frequency plot, you will see that anything in the lower frequency range will suffer from 1/f noise. This is what is dominating for low frequency. However, for high frequency, the thermal noise becomes dominant. Okay, so thermal noises are mostly because of the random carrier motions and etc., which creates a thermal noise. However, for high frequency it becomes dominant. However, for low frequency we say it as 1/f. So you will find that noise is also related to GM. I am not going much into details into the noise at this stage. There are noises where you will find that GM is directly related, or sometimes it is related to GM square. That means if you are increasing GM, as I have said, which will increase gain, which will also increase noise. So gain and noise both are increasing together. Again, there is a problem. So there are many things you have to take into the consideration. So I am not going in much details into the noise here, but there are relations wherein noise is related to GM. Now there are different design parameter adjustments as well. So you have to adjust different design parameters. I have said different design parameters. And now there are adjustments are required. For example, say increase VDD or tune I bias. I already have said the biasing has to be tuned, otherwise you may not stay in the linear domain. One issue. In certain, as we progress, we'll see that even if you don't tune the bias, you may reach in the you will no longer be in the active region for BGT. For example, you want to operate the device in active region, increase the bias, you'll go into the situation which is not desired. So there are more complications, but here, as I have given you one example, so I am repeating this, that if you don't tune those parameters, you may not get a very good response from the circuit. So stabilizing DC biasing, stabilized DC biasing is important. Even if your bias is not stabilized, if it is moving here and there while operation, it will create another problem. Sometimes you will get good signal, sometimes you won't get good signal. So it's kind of a drift. I said, if with time it is drifting, and after some time you will find that your circuit is not working properly. So this is a problem. Then designed for comfortable PM. PM means, what is PM? PM means phase margin. What is phase margin? Phase margin means if you have a signal, say V equal to V0 sine omega t plus phi, then this is what we call as phase. Now say after some time phi have become phi 1, the phase has changed. So this phi, the difference between phi and phi 1 should not be very high. There should be a margin. It may happen that not only the other parameters, phase is also changing. So you should consider that phase margin as well, that your signal is changing in terms of phase as well. So you should have a comfortable phase margin. It should not be a very high change in phase that you lose the signal at the output. Then you have pole zero compensation. This pole zero you will find in control system course. I am not going much details into it, but just to give you an idea, pole zero is related to the stability of a system. Now it should not happen that your system is not stable. And what does it mean physically? Is not stable? Is not stable means, say you have designed a circuit for a particular gain, and you see that with change in frequency or something, the gain is also changing. So it's a problem then. It's not a stable system. If your gain also changes with different parameters, then it's not a very good system to use. So that parameters we have to take care. So same goes for the GM also. So constant GM architecture means GM also should be stable. It should not vary too much while in operation. In fact, ideally it should be constant always. These parameters, the gain, GM, all these things. Then use differential structure and offset compensation. Offset compensation means, again, offset is related to drift. If something is drifting, that compensation should be there. Okay. So I told you that thermal compensation circuit, there might be a drift due to temperature generation, which in many cases you'll find, especially for, say, you are designing something related to temperature, for example, say circuit for temperature sensor, this and that. So in that case, it may happen that your signal is drifting, and it will create an offset. Offset means what is desired is not coming. There is a gap between this, and that offset compensation should be there. So offset compensation circuits are also important. So you have to take all these adjustment into the consideration while designing. Okay, so this is what I was saying for long, a multi-dimensional trade-off. So noise, linearity, gain, supply voltage, voltage swing, speed, input-output impedance, power dissipation, all are connected. So it is known as analog design octagon. You change something, this will change something else. So these are the challenges that you have to keep in your mind while designing the analog circuit. So remember this, this octagon. This will give you a better idea of what multi-dimensional trade-off is all about. Okay. So there are also challenges in mixed signal CMOS circuits. So that part is also very important.